Let's start with the number 4. As we know, 4 is equal to 2 squared. Now, if we replace all the 2's with 3's and then subtract 1, we get 26. Now expand 26 in pure base 3. If we replace all the 3's with 4's and then subtract 1 again, then we get 41. Now let's expand 41 in pure base 4. If we replace all the 4's with 5's and then subtract 1, then we get 60. If we continue this process, it seems like the numbers keep increasing. However, the sequence actually eventually goes to 0. The number of steps you need to take is about 121 million digits long. Sequences generated in this way are called Goodstein sequences, and it turns out that every Goodstein sequence goes to 0 after finitely many steps. But you might be wondering how I calculated the exact length of the Goodstein sequence generated by 4. Even if I had a supercomputer that could generate 1 quintillion terms per second, it would still take me over 10 to the 100 million years to see the sequence reach 0. Well, you probably looked it up on Wikipedia. The fact that every Goodstein sequence is finite was proven in a previous video. This is a very polite way of saying that this video is a follow-up, and you should definitely watch the last one. What, you're not gonna? Fine. Here's a TLDW that will probably be good enough for our purposes. Before we can recount, we need to count. In fact, we need to count so hard that we count past all of the finite numbers, bringing us into the wonderful world of ordinals and their arithmetic. I have a video where I talk about this stuff in much more detail, but we've already decided we're not watching my other videos right now, so just trust me that you can add, multiply, and exponentiate with ordinals, and it's almost natural. Of particular importance for us right now is omega, the first infinite ordinal. For every finite number n, we can use omega to describe the shape of its expansion in some base b, which we'll call Rb omega of n. The big idea behind the proof is that, although the terms of a Goodstein sequence themselves don't seem to be decreasing, their corresponding shape ordinals do. Although these shapes generally take infinite ordinal values, any strictly descending sequence of ordinals is necessarily finite by well-foundedness. Therefore, the same is true for the corresponding Goodstein sequences. Since the length of a Goodstein sequence is completely determined by the decreasing sequence of ordinal shapes, we can redirect our attention to studying how these ordinals behave instead. For the Goodstein sequence generated by 5, I've organized the terms into chunks. In each of these chunks, subsequent ordinals are easy to guess. The ordinal after is just the result of subtracting 1. Simple enough. In these cases, we can say that Rb omega of n minus 1 is equal to Rb omega of n minus 1. The non-trivial part is when we transition between chunks, which happens when the finite term of the ordinal is 0. These ordinals are called limit ordinals, for reasons that aren't relevant right now. But these are exactly the ordinals where subtracting 1 doesn't make any sense. For the smallest example, suppose you wanted to subtract 1 from omega. If we could, then we would get some ordinal that's strictly smaller than omega. However, by definition, omega is the smallest ordinal larger than everything finite. Therefore, omega minus 1 would have to be finite, but this would make omega 1 larger than a finite number, and therefore finite itself. But that makes no sense. Therefore, we conclude that omega minus 1 just doesn't make sense. So if we can't subtract 1 from Rb omega of n, then how do we predict the next ordinal? Let's try to understand what's happening on the Goodstein sequence side. In fact, let's just remind ourselves how to subtract finite numbers by 1. If the least significant digit is positive, then you just subtract 1 from that digit. However, if the least significant digit is 0, then we need to borrow from the digit ahead of it. Or at least, that's what your grade school teacher told you. But why is that true? Justifying these borrows amounts to some straightforward algebraic manipulation. We are splitting the decimal expansion to reinterpret one of the next available digits as an illegal least significant digit. This reinterpretation does not affect the value of the expansion, but it makes subtracting 1 as easy as the first case. When we identify a number with the ordinal shape of its expansion in decimal, we are basically viewing omega as a stand-in for 10. So what does this act of borrowing do to the shape of our decimal expansion? Well, it decrements the next available digit, and reinterprets this digit as an illegal digit of value 10. Now we no longer have a limit ordinal. In particular, we can subtract 1 from it. Moreover, this difference is exactly the proper base 10 shape of the original number minus 1. Now that we have the big idea, let's explain in general how to set up an ordinal alpha for a base k borrow. First, write alpha out in Cantor normal form. Note that since alpha is a limit ordinal, the least significant digit is 0. Now, to borrow from the next available digit dm, we just subtract 1 from dm and view the resulting omega to the xm as omega to the xm minus 1 times k. We may be able to subtract 1 from dm since dm is finite and positive, but xm might be infinite, so we can't necessarily subtract 1 from it. This may seem like a problem, but fret not. If we can subtract 1 from the exponent, then just do it. Otherwise, just recursively set up the exponent for a base k borrow instead. Now, on top of being set up for base k borrows, you can also think of alpha k as an order k approximation of alpha. For example, the base k prep for omega just gives you k, and omega is in some sense the limit of all of these k's. Similarly, the base k prep of omega squared is omega times k, and omega squared is in the same sense a limit of the omega times k's. This interpretation also makes sense in general. In fact, the sequence of alpha k's has a special name. It's called the Wainer fundamental sequence of alpha. With the mechanisms for borrowing digits, we can talk about a base k predecessor of an ordinal. If we have an ordinal alpha where subtraction by 1 makes sense, then define the base k predecessor of alpha to be its actual predecessor. Otherwise, we'll borrow in base k and then take the base k predecessor of the result recursively. It helps to do an example, so let's compute the base 3 predecessor of omega to the omega together. And there we go. Notice that the answer is analogous to how 3 to the 3 minus 1 is 3 squared times 2 plus 3 times 2 plus 2. Of course, this is what we expected. This may not be the most efficient procedure for computing a base k predecessor, but you know how mathematicians are with programming. If you're a mathematician insecure about your programming skills, you can shed that insecurity with the help of today's sponsor, Brilliant. Brilliant is where you learn by doing, with thousands of interactive lessons in math, data analysis, AI, and of course, programming. With the help of Brilliant's course on Thinking in Code, where you can learn all of the essential concepts of programming, you can be well on your way to implement Goodstein sequences in everyone's favorite programming language, Python C++. Though for real, it's probably for the best to implement Goodstein sequences in Python instead of C++, since the C++ standard doesn't have any support for arbitrary precision integers. No matter what tickles your fancy, Brilliant can come up with a plan to help you meet with your learning goals, from wherever your starting point is. To try everything Brilliant has to offer, free for 30 days, visit brilliant.org/gsheaf, or click on the link in the description below. By following the link, you'll also get 20% off an annual premium subscription. Thank you so much to Brilliant for sponsoring this video. By design, our base k predecessors give us an explicit formula for the shape of each term in a Goodstein sequence. Now, instead of asking for what finite n do we have gn is equal to 0, we can instead ask for what finite n do we have that the base n predecessor of the base n minus 1 predecessor of the base n minus 2 predecessor, so on and so on, until the base 3 predecessor of R2 omega of n is equal to 0. This problem might seem just as difficult, but we can make our lives much easier by making the problem more general. By fixing some finite positive number b and some ordinal alpha, for what finite n greater than b do we have that the base n predecessor of the base n minus 1 predecessor all the way to the base b predecessor of alpha is equal to 0? Now, if we want to answer this question with a formula, we're going to need some really fast-growing functions. So how would you define a really fast-growing function f from the natural numbers to the natural numbers? The key to success is to control your expectations. And you can't spell success without suck. The successor function is probably the most natural place to start, so let's call that f0. Now that we have f0, how do we make it faster? Well, the easiest way is probably just to repeat f0 several times. If we repeat f0 on n a total of n times, then this function amounts to doubling n. Let's call this function f1. Want to make it even faster still? We'll just apply f1 a total of n times on n. Now, instead of doubling, we're multiplying by 2 to the n. If we keep repeating this procedure, we get some really fast-growing functions. So can we extend this sequence to omega? Well, we still want the function to map natural numbers to natural numbers. So one way we could achieve this is by defining f omega of n to be fn of n. Notice that this is the same as taking the subscript to be the nth term of omega's fundamental sequence. For example, f omega of 3 would be equal to f3 of 3, and if we expand that, then we get interesting. Anyway, by using fundamental sequences, we can extend this procedure much further, getting fast-growing functions indexed by infinite ordinals. Note that despite the fact that alpha is possibly infinite, f alpha of n is always finite for every n. However, this function f alpha grows almost incomprehensibly fast as a function of n. In fact, these functions define what's called a fast-growing hierarchy. Now that we have a hierarchy of fast-growing functions, we can figure out exactly how quickly the length of a Goodstein sequence grows. Let's recall that we're answering this question by instead answering a much more general question. It turns out, for any finite positive b and any ordinal alpha, if we write alpha in Cantor normal form, then the base n predecessor of the base n minus 1 predecessor all the way down to the base b predecessor of alpha is equal to 0 once n is equal to fc1 of d1, fc2 of d2, all the way to fcm of dm of b minus 1, where these f's are part of our fast-growing hierarchy. With this theorem, we'll be able to calculate the exact length of the Goodstein sequence generated by 4, but we'll hold that off until we earn it by proving this theorem in the first place. As seems to be the case in this channel a lot, we'll prove this by induction on alpha. If alpha is equal to 1, which is just omega to the 0 times 1 in Cantor normal form, then the base b predecessor of alpha is just the actual predecessor of alpha, which is 0, and b is exactly what the theorem predicts for n. This proves the base case for all positive finite b. Now for the induction, let's assume that the theorem is true for every positive ordinal that is smaller than some alpha. Then we have two cases. In case 1, alpha minus 1 makes sense. This means that the Cantor normal form of alpha has a positive finite term. In the second case, alpha is a limit ordinal, which means that the Cantor normal form has no finite term. In the first case, if alpha minus 1 makes sense, then the base b predecessor of alpha is just alpha minus 1. Let's call this predecessor alpha prime. Then, by definition, alpha prime's Cantor normal form will be the same as alpha's, except that the last digit is 1 smaller. Since alpha prime is smaller than alpha, the induction hypothesis tells us that the base n predecessor of the base n minus 1 predecessor all the way down to the base b plus 1 predecessor of alpha prime is 0 once n is equal to this. If we recall that f0 of b is equal to b plus 1 by definition, then this innermost piece is exactly equal to dm applications of f0 on b. If we unwind the definitions a little bit, we'll realize that this actually proves that the theorem is true for alpha. This handles case 1, so now let's look at case 2 when alpha is a limit ordinal. In this case, the base b predecessor of alpha is by definition the base b predecessor of the base b borrow of alpha. Let's call this base b borrow alpha prime. We've already studied what the base b borrow of an ordinal is supposed to look like, and we have two cases depending on if the smallest exponent of omega is a limit ordinal or not. Either way though, we're golden. Since alpha prime is necessarily smaller than alpha, induction tells us that the base n predecessor of the base n minus 1 predecessor all the way down to the base b predecessor of alpha prime is equal to 0 exactly when n is equal to this. Although this innermost piece has two cases depending on xm, you can check that each of these cases is actually equal to fxm of b, and this falls right out by the definition of our fast-growing hierarchy. In particular, by unpacking the definitions again, we see that this second case also implies that alpha must satisfy the theorem. Since both cases imply that the theorem holds for alpha, it follows by induction that the theorem is true for every alpha. Now let's reap the rewards and calculate the explicit length of any Goodstein sequence. To calculate the length of the Goodstein sequence generated by a number n, we first write n in binary. Now if we take these exponents and plug them into this formula, then this formula will calculate for us the exact length of the Goodstein sequence generated by n. Let's use this to calculate the length of the Goodstein sequence generated by 4. Since 4 is equal to 2 squared, this result tells us that the length of the Goodstein sequence generated by 4 is equal to f omega of 3 minus 2. Recalling the definition of the fast-growing hierarchy, we can simplify this expression step by step until we get to the number that I claimed at the beginning. If you're still here, thank you for watching. If you like what you watched, there's something you could do to bring me one step closer to having f omega of 64 subscribers. If you didn't like what you watched, I think I can guess why. You must be wondering why, for the past 2 videos, I forced you along this long and winding road through the ordinal numbers just to prove a finite fact about finite numbers. Why not just prove this with plain old finite numbers? Well, there's actually a good reason why not. These fast-growing functions are not just fast, they're really fast. In fact, if you program some function g and you use these rules below to prove that your function must terminate on every input n, then it is inevitable that your function will grow slower than some functions in this fast-growing hierarchy. On the other hand, we just proved that the length of a Goodstein sequence is calculated by iteratively applying these fast-growing functions. This means that the length of a Goodstein sequence, as a function of n, grows faster than f alpha of n for every ordinal alpha. Therefore, it's impossible to use the first-order theory of natural numbers to prove that the length of every Goodstein sequence is finite. In some extremely loose and imprecise sense, this means that it is inevitable that a proof of Goodstein's theorem requires tools beyond that of finite arithmetic. If you're still not happy, that's fine. The number of fans who've got my back will always have a well-defined predecessor.